Welcome to The Explainer. Today we're diving into a really profound idea. What if an AI could do something no other program can? What if it could rewrite its own code to become provably, perfectly better? We're going to explore a concept called the Gödel machine, inspired by, you guessed it, the legendary logician Kurt Gödel.
So to really get why the Gödel machine is so wild, you first have to understand a limitation that's baked into pretty much all software. You see, a traditional AI, even a super powerful one, is basically stuck with the core logic its human creators gave it. Sure, it can learn, but it can't fundamentally change how it learns. The Gödel machine is a whole different beast. It's designed from the ground up to be able to rewrite its own source code. I mean, any part of it, even its most fundamental learning algorithms.
And this limitation? It's often called the grand problem of AI. Even our most advanced systems are, when you get right down to it, hardwired. They can learn from data, for sure, but they can't improve their own core method for solving problems. For that, a human programmer has always had to step in and design a better algorithm from the outside. Well, this leads to a really fascinating question. What if a program could finally break that cycle? What if it could improve itself not just by tweaking a few numbers here and there, but by rewriting its own foundation in a way that's mathematically, provably better? This is the exact problem that computer scientist Jürgen Schmidhuber set out to solve with a pretty radical concept he proposed way back in 2003.
And that brings us to his solution, the Gödel machine. The big idea here is to create a system that can perform the ultimate act of self-improvement, literally rewriting its own source code.
Now, the crucial point here is that the machine doesn't just change its code randomly or on a whim. Nope. It operates on a principle of provable optimality. It's a universal problem solver that can rewrite its own software. But, and this is a huge but, only with a critical safety catch. It must first find a mathematical proof that the change is a genuine improvement towards its ultimate goal. This isn't just learning or adapting. This is provably optimal self-evolution. Okay, so you might be thinking, how could a machine rewrite itself without immediately breaking down or getting stuck in some terrible loop of bad updates? Well, the answer lies in a very disciplined, proof-gated process.
The machine basically runs on a simple but incredibly powerful three-step loop. First, it searches. It's constantly looking for potential code changes, which are called switch progs, and at the same time, it's looking for proofs that these changes are actually beneficial. Second, it has to prove its case. It has to find a formal mathematical proof that making a specific change right now will create a better future than just continuing on its current path. And third, only if that proof is found does it execute the change and rewrite its own software. That proof is the ultimate gatekeeper. No proof, no change. Simple as that.
And these three core components work together almost like a little self-governing system. First, you've got the axioms. Think of these as the machine's constitution, the fundamental, unchangeable rules about its hardware and software. Then there's the utility function, which is basically its prime directive, that single, ultimate goal that every single action is measured against. And finally, you have the proof searcher, which acts like a constitutional lawyer, tirelessly searching for proofs to argue for or against changes to its own code, all based on that constitution and that prime directive.
And this whole system enables the machine's most profound feature, something called global optimality. This is really what separates it from a simple algorithm that just makes whatever change looks best at any given moment.
You see, the proof it's looking for isn't just that a change is good. The proof has to show something much, much stronger. It has to prove that the benefit of making the change right now is greater than the benefit of waiting for an even better change that its unmodified self might find down the road.
And that is a massive leap. It's the difference between, say, picking the first good apple you see versus knowing for a fact it's the best apple you can provably find in the entire orchard. The machine avoids getting stuck on a small hill of improvement, what's called a local maximum, because it has to prove its next step is on the path to the highest provable peak.
But, as that name, Gödel machine, suggests, its greatest strength, its total reliance on mathematical proof, is also the source of its most fundamental limitation.
Yeah, if this all sounds a little too perfect to be true, well, your intuition is spot on. The catch lies in the work of Kurt Gödel himself.
Gödel's famous incompleteness theorems basically state that in any complex formal system, like math, there will always be true statements that you simply cannot prove. And that exact same logic applies here. The Gödel machine can only make improvements that it can formally prove are useful. So what if a brilliant, game-changing upgrade exists, but the proof of its value is just unprovable? Well, the machine can never implement it. It is fundamentally blind to truths it cannot prove.
So,
Given these incredible possibilities and, these pretty deep limitations, why does this theoretical concept even matter? What does it really tell us about the future of AI?
It matters because it gives us a blueprint for a truly self-improving artificial general intelligence. It turns these abstract ideas like self-awareness into a concrete technical challenge. Can a system look at its own code and rewrite it for the better? It could optimize anything from its own software slowdowns to proving it should build better hardware for itself. And maybe most profoundly, it could even modify its own goals as long as it can prove that changing its goals is the optimal move according to its current goals. The Gödel machine really frames the ultimate AI challenge not just as learning, but as recursive, provable, and globally optimal self-improvement.
And that leaves us with a final, pretty provocative thought. If we could actually build an AI that can provably improve every single aspect of itself, its code, its hardware, even its own goals, what would its final form even look like? I mean, where does a journey of infinite optimal self-improvement actually end?
Welcome back to the Deep Dive. This is the place where we break down some of the most complex, most ambitious research in the world and try to turn it into something we can all grasp.
And today, we are really going to the edge. We're talking about the theoretical limits of artificial intelligence itself, the concept of a universal problem solver.
Right. And we're not just talking about an AI that can learn a new task. We're getting into what some people call the grand problem of artificial intelligence.
Which is, how do you create a system that doesn't just learn within its given framework, but actually learns how to improve that framework? How it can rewrite its own fundamental algorithms, all without a human stepping in.
Exactly. So, forget about a machine learning model just tweaking its little coefficients. We are talking about an AI that can literally look at its own source code and say, you know what? This entire operating system you gave me is inefficient.
And not only is it inefficient, but I am now going to mathematically prove that my new design is superior and that I'm going to install it myself.
Which is just a mind-bending concept. So the mission for this deep dive is to really get our heads around the Gödel machine.
A theoretical concept, of course, named after the legendary mathematician Kurt Gödel. It's a whole class of, well, mathematically rigorous, self-referential, and optimally efficient problem solvers. And it draws directly on the work he did nearly a century ago.
Okay, so let's just state the core idea right up front because it's revolutionary. This machine only rewrites its own code, its own foundation, when it has formally, mathematically proven that the change will be useful. No guesswork.
Guaranteed. And that capability, that self-referential proof search, is the direct link. It connects modern AI theory all the way back to Gödel's incredible self-referential formulas from 1931.
So if you want a shortcut to understanding what superintelligence could actually look like from a rigorous mathematical perspective, this is it. This is the deep dive for you.
Let's get into it.
Okay, so let's start at the beginning. Why do we even need something like this? What is the core limitation of, every AI we use today?
Well, if you look at the entire landscape of modern AI, deep reinforcement learning, search algorithms, optimization methods, you name it.
All of them.
Right, all of them. They all share one fundamental restriction. Their core logic is hardwired.
Meaning they're stuck. They're structurally stuck with the rule book we gave them at the start.
Precisely. A model from, say, DeepMind can get incredibly good at a game. It can find the optimal strategy. But what it can't do is look at the algorithm it's using, like Q-learning, and decide, this whole approach is flawed. I'm going to invent a totally new, superior way to learn.
It can't become an algorithm creator. It's just an executor.
Exactly. And so humans are still in the loop for the big leagues. We have to design the new, better algorithms. And this is the critical part. We have to prove their usefulness. That can take years of theoretical work before they're ever deployed.
So the Gödel machine is designed to automate that entire scientific process, the discovery, the validation, the implementation, all of it.
It's meant to be a truly universal problem-solving system. You can imagine it living in some environment, which could be incredibly complex, maybe only partially observable, maybe random. And its single greatest power is that it can modify itself in any computable way imaginable.
And its entire life is governed by this one really powerful rule, the self-modification rule. How does that work in practice?
So the initial algorithm, let's call it B, that's the machine's starting point. But unlike traditional AI, this program is not sacred. It's not untouchable.
Just version 1.
It's just version 1. It includes maybe a suboptimal way of interacting with the world, but most importantly, it contains the initial proof searcher. And the ironclad rule is this. Any rewrite, any fundamental change to PLA can only happen if that proof searcher, which is embedded inside it, can first prove that the new program,
The proposed upgrade.
right, what the paper calls the switch prog, it has to prove that the switch prog will actually increase the machine's future success.
It needs a mathematical, undeniable, formal proof that the future with the new software is better than the future with the old software.
And that idea of future benefit is completely formalized. It's all captured in the machine's utility function. Its ultimate singular goal is to maximize future success or utility. Let's call this function OGRA.
Okay, let's drill down on this utility function, OGRA, because it seems like this defines the machine's entire purpose, its whole value system. How do you quantify utility?
Conceptually, you can think of dover hours as the value to go. It's a calculation of the expected cumulative future reward minus the expected cumulative future cost.
So everything it might gain balanced against everything it will cost to get there.
Exactly. And there are a few key components in that idea. First, it's an expectation. That means it has to account for probability, for uncertainty. If the world is random or unpredictable, the machine is trying to maximize its most likely positive outcome.
Okay, that makes sense.
And here is the really critical part. This utility function includes the computational cost of everything.
Everything, like even the cost of thinking.
Even the cost of thinking. The time and energy spent running the proof search itself is a cost. If it's a robot, the physical energy to move an arm is a cost. Even the basic hardware instructions, every single clock cycle has a tiny cost associated with it. It's all factored in.
Wow. So the machine is literally penalized for wasting time thinking. It can't just go off on some infinite philosophical proof search that never produces a result.
It can't afford to. Its value system pushes it to be efficient. The cost of its own thought process is baked into its core goal. It has to find useful proofs, and it has to find them in a way that doesn't waste more resources than the proof is worth.
That's fascinating. So this machine, it operates in discrete time steps, right, on some kind of abstract computer model. What does its internal state, what the paper calls Dipper, actually look like? What data does it need to keep track of to even begin to reason about itself?
The entire state has to be a snapshot of everything the machine needs to know about itself and the world at a given moment. You can really break it down into 4 essential buckets of information, all stored as bit strings.
Okay, what's the first one?
A simple, unique binary representation of the current time step, $2. It starts at 1, and the hardware just keeps ticking it up. This is critical because its utility is time-dependent. It has to reason about what's better to do now versus what it could do a million cycles from now.
Makes sense. Second.
$6. The sensory input. This is how it sees the world, how it gets information, how it receives those reward signals from the environment.
And third, there must be an output.
Right, the outputs that let it influence the environment, the control signals for its actions. If it's a robot, this is the command to move its arm.
Okay, time, input, output, standard stuff. What's the fourth piece?
This is the mind-bending one. $2. The initial software program itself.
Wait, the program is stored inside its own working memory.
It has to be. The program, P, $2, which contains that initial policy and the proof searcher, has to be stored within the state, $. It has to be readable and modifiable. Without the ability to read and reference its own code, its own blueprint, how could it possibly reason about the consequences of changing that code?
It needs a mirror.
It needs a perfect mirror. Self-representation is the absolute, non-negotiable prerequisite for this whole thing to work.
Okay, so that sets the stage. The machine exists in time, it sees, it acts, and it holds its own blueprint. Now, let's get into the complexity. How does it actually reason? How does it build a proof? We need to understand its foundational logic.
Right, so the entire reasoning architecture is built on what's called an axiomatic system. Call it a dollar.
Okay, an axiomatic system, like the axioms of geometry.
Exactly like that, but vastly more powerful. This system, a dollar, is a huge set of formalized rules that are encoded in that initial software. It gives the machine its formal logic, its mathematical tools, really its definition of reality.
So we're talking about a formal system that's strong enough to include, what, standard arithmetic, probability theory?
All of that. And calculus, string manipulation, basically all the tools you would need to rigorously calculate the expected utility of some change in a messy probabilistic world.
The source material groups these axioms into 6 categories, but maybe we can simplify that. What are the big conceptual blocks it needs to know?
I think we can boil it down to 3 big ideas. The machine needs to know about itself, it needs to know the rules of the world, and it needs its language of reason.
Okay, let's start with itself, its own constitution.
Right. This block would include the hardware axioms, and the initial state axioms. These are formal specifications of how the hardware works, how the state changes from one cycle to the next.
So an axiom that says, when this instruction is executed, the instruction pointer increases by 1. That kind of detail.
Exactly that level of detail. It's the physics of the machine itself, written down as mathematical truth. And it also includes the specific starting conditions, the state at time equals 1. The machine starts with a perfect, undeniable truth about its own physical makeup and initial memories.
Got it. What's the second block? The rules of the world.
This covers the reward axioms and the environment axioms.
Okay, so reward axioms define what's good and what's bad.
Precisely. They define the costs of instructions and actions, like we talked about. But more importantly, they define how reward is received from the world. An axiom might say, when input 11 is received, the cumulative reward increases by 3. It's the value system.
And the environment axioms.
They place limits on how the environment can behave. For example, an axiom might state that the environment is drawn from some unknown but computable probability distribution. It's the machine's initial set of assumptions about how weird the world can get.
Like it assumes the laws of physics won't just randomly change.
That would be a very good axiom to have, yes. And finally, the third block is the logic toolkit. This is where you find the uncertainty axioms and the utility axioms.
So this is the standard math stuff.
Yeah.
Probability, calculus.
Right, the tools it needs to reason about uncertain futures, and of course, the formal definition of the utility function, $2 itself, the ultimate goal.
Okay, so our dollars is this massive, self-contained mathematical universe. How does the proof searcher actually use it to build a proof?
The initial proof searcher doesn't just randomly throw axioms together. It uses what the paper calls proof techniques. You can think of these as little specialized algorithms or strategies for generating a proof. They are programs inside dollars that can read the machine's state, define a potential new switch prog, and then start generating a sequence of theorems.
And what special tools do they have? What are the instructions that make self-reference possible?
There are 6 critical instructions, but again, we can group them. First, you have the basic proof-building tools.
Like get axiom.
Right. Get axiom pulls a foundational rule from a ternal dollar. Apply rule uses an inference rule, like modus ponens, to combine existing theorems. And delete theorem is just for housekeeping, to free up memory.
Standard stuff for a theorem prover. What's the next category? This seems to be the game changer.
It is. The second category is self-observation, and this is really one instruction. State to theorem.
State to theorem, what does that do?
It's absolutely crucial. It lets a proof technique look at a specific section of the machine's own memory right now and turn that observation into a time-labeled theorem, a formal, verified truth.
So it can say, for instance, at time step 7775555, the bits in this specific register were 1001, and that becomes a new axiom it can use in its proof.
Essentially, yes. It accepts its own current observable state as a self-evident truth. It creates, as the paper calls it, an online interface between syntax and semantics.
I don't get it. Why is that so important? Why can't it just look at its own memory whenever it wants?
Because this formally grounds the abstract proof system in the machine's current reality. It allows the machine to use knowledge it has already gained from the world or from a previous computation without having to rederive that knowledge from first principles, starting from C's every single time. It's a massive shortcut.
I see. But the source points out a huge problem here, the self-observation problem. What happens if I try to read a variable that's changing really fast, like the instruction pointer itself? The act of reading it might take a few clock cycles, and the value could change in the middle of the read.
You've hit on it. You could generate an inconsistent theorem, a lie about your own state. It's the closest thing this field has to a Heisenberg uncertainty principle. The act of observing the state can interfere with the state you're trying to observe.
So how does the Gödel machine not lie to itself? How does it solve this?
The state-to theorem instruction has a very clever protocol built in. Before it translates a memory section into a theorem, it first checks if that section is stable and readable. If it's a highly volatile part of the hardware that can't be read reliably in a single atomic step, the instruction just fails. It refuses to create a potentially contradictory truth.
So it only accepts observations it can guarantee are consistent.
Exactly. It's an incredible level of self-scrutiny to ensure its own reasoning is sound.
Okay, so we have proof building and self-observation. What's the last set of instructions?
The third category is control flow. This includes set switch prog, which is how it nominates the new program code, and then the final, most important one, the gatekeeper instruction, check.
And check is the one that pulls the trigger.
That's it. Check looks at the very last theorem generated in the proof. If that theorem is the specific target theorem it's looking for, it sets a special switch bit to 1, control is transferred to the switch prog, and the self-rewrite actually happens. It's the only way a change can occur.
So everything hinges on proving this one specific target theorem. What does that theorem actually have to state?
We can define it pretty simply. The target theorem must be a formal proof of the following statement. The utility of the state with the switch activated is strictly greater than the utility of the state with the switch not activated.
Okay, let me try to translate that. The machine has to prove executing this new program, starting right now, is unequivocally better for my entire future than just carrying on with what I'm currently doing.
That is precisely what it has to prove. And that leads us straight into the most critical and, frankly, the most surprising result of the whole Gödel machine concept.
Yeah, this brings up the elephant in the room, the thing that sounds like a paradox.
The paradox of self-improvement.
Right. When the machine finds a switch prog and proves it's better, that feels like a local search, a greedy optimization. You know, what if the current program, POD, is really good at finding small, easy improvements? It might find one, make the switch.
And in doing so, it terminates the search that could have led to a much bigger, more revolutionary improvement that the old program would have found if it had just kept running for another week.
Exactly. How does it avoid getting stuck in a local maximum? If it can only prove that switch prog A is better than what it has now, how does it account for the potential of a switch prog B that it might have found tomorrow?
This is where the mathematical rigor of the system really pays off. The answer is in the global optimality theorem. This is a theorem 4.1 in the paper, and it guarantees that any self-change that happens via a proof of that target theorem is, in fact, globally optimal.
Okay, I need the aha moment here. Walk me through it. Why isn't this greedy?
Because of how the two sides of that inequality in the target theorem are defined. The decision is fundamentally binary, and the terms are utility functions that look at the entire future.
So option A is execute this switch prog right now.
And option B is don't. Keep searching for other proofs and other switch progs using the existing program, p-Agors.
Okay, I think I see it. The key has to be in how it calculates the utility of option B.
You've got it. The term text state with switch not activated isn't just the utility of doing nothing. It is calculating the entire expected future utility of continuing the existing search process.
Whoa, so that calculation somehow includes the possibility of finding that revolutionary switch prog B next week.
It has to. That term implicitly includes all subsequent, possibly infinitely many, better alternatives that the unmodified program proters might discover later on. It's a probability-weighted value of every future the current program could lead to.
So the machine isn't proving this change is better than doing nothing. It's proving this change is so good that its value is higher than the entire expected value of continuing my search for anything else.
That's the aha moment. The switch prog is only executed if it's proven to be better than waiting. If waiting has a higher expected utility because there's a good chance of finding something even better, then the proof of the target theorem cannot be completed. The inequality isn't true.
That is profoundly elegant. It just collapses this infinite tree of future possibilities into one single comparison.
And this also solves another huge conceptual problem in AI, the problem of meta levels.
Right, the bootstrapping problem. If I have an algorithm that improves my learning, what algorithm do I use to improve that algorithm? And what improves the improver? You get this infinite regress.
The Gödel machine avoids that with what's called the recursive collapse. A proof of a target theorem automatically proves that the self-modification is beneficial for all subsequent self-modifications that are affected by it. It's all baked into that one utility calculation. There are no meta levels, just one level, which is total self-reference.
So if the change is provably optimal now, it's also provably setting the stage for the optimal path of all future self-improvements.
Within its axiomatic system, yes. It's a complete theoretical solution.
The source also mentions a relaxed version of the target theorem, right? Using a greater than or equal to sign.
Yes, exactly. A slight modification where the machine will make a change if it can prove the utility is at least as high as waiting.
So if the expected payoff is identical, it prefers to act now rather than keep searching.
Right. It's a bit less demanding on the proof searcher. It just has to prove non-negative utility gain. And this version also maintains global optimality, so it's a valid alternative.
Now we're talking about formal proofs. How often does this process just hit a wall? Run into the fundamental limits of what's provable?
All the time. And that's a feature, not a bug. For simple tasks, the proof can be trivial. If the machine is stuck in a 5-hour setup phase, but sees a lever that gives maximum reward, the proof it's useful to interrupt the setup and pull the lever is probably very short.
But for more complex self-improvements.
For complex ones, you slam right into Gödel's incompleteness theorems, Rice's theorem, Bloom's speed-up theorem. There will always be potentially useful changes whose utility is simply unprovable within the axiomatic system dollar.
And in those cases, what does the GM do?
It ignores them. It has to. Its optimality is constrained by what is provable. The beauty of the system is that it accepts this. If the machine itself cannot prove a change is useful, the assumption is that a human probably couldn't either, given the same axioms. It only acts on certified, proven improvements.
Which is a huge advantage. It can at least find and exploit all the provably good speedups, which leads us to how this compares with other theoretical systems.
Right, which gets us into the weeds of computational complexity, specifically the idea of domination.
Okay, let's break this down. The initial proof searcher in the Gödel machine is designed to be as good as it can be from the start. It uses a method called bias optimal proof search, or BIOPS.
Correct, and BIOPS is what's called optimal.
Right, optimal. For anyone listening who isn't a computer scientist, why is this notation so important here?
It's crucial because it describes how an algorithm's runtime scales as a problem gets bigger. An optimal algorithm is, in a sense, asymptotically the best. It means if there's some secret genius technique that can solve a problem in, say, 5-day steps, BIOPS is guaranteed to find a solution in a runtime that's on the same order of complexity.
Absolutely. So in a race that goes on forever, it's guaranteed to keep pace with the best possible solution.
Exactly. But here's the billion-dollar catch. The dollar notation, by its mathematical definition, ignores constant factors, and that is the fundamental flaw when you try to apply pure optimality to the real world.
Okay, so talk about these constant factors. How big of a slowdown are we actually talking about here?
In other theoretical systems, like Hutter's AIXI or Levin's universal search, which are also optimal but are hardwired, these constant factors can be astronomical.
Like twice as slow, 10 times as slow.
Try a number larger than 10 nanodollars.
What? That's not a constant factor. That's a universe-ending delay.
It renders this system completely useless for anything practical. Here's an analogy. AIXI is like having a perfect mathematical formula for building the fastest spaceship imaginable. It's optimal, but the formula requires you to spend 10,000 years just calculating the first line of the code for the launch sequence.
So the theory is perfect, but the startup cost is so high that the universe will have ended before it does anything useful. And because it's hardwired, AIXI can't do anything about that 10,000-year calculation.
It's stuck with it forever. Now, compare that to the Gödel machine. Its utility function, to-on, explicitly penalizes wasted time. It does not ignore huge constants. Therefore, the GM can look at its own 1,000-year-long startup sequence and search for a proof that says, if I rewrite this one subroutine, I can reduce that startup time by a factor of 10 hours.
And because that massive time saving leads to a provably higher utility, it executes the rewrite.
And that's the core difference. The GM moves beyond the purely theoretical optimality to a practical, constant-aware optimality.
Okay, let's really spell out the key advantages the GM has over a system like AIXI. You've mentioned the first one. The searcher itself is modifiable.
Right. AIXI's searcher is a fixed bottleneck. The GM's proof searcher is just part of the software, readable and modifiable like anything else. It can recursively optimize itself.
What's the second big difference?
The source of their optimality. AIXI's optimality comes from a clever but fixed time allocation rule given to it by its human designer. The GM's optimality comes from the self-referential proof that a change is the best possible action. It doesn't rely on a fixed rule. It relies on adaptable, provable logic.
And a third difference is flexibility.
Yes, AIXI is designed to maximize one thing: expected cumulative reward. The Gödel Machines framework is more general. You could give it any formalizable utility function. You could tell it to maximize worst-case reward or to maximize its own survival probability, or even something abstract like maximizing the complexity of its environment. The self-modification logic works for any well-defined goal.
It's a universal framework for goal achieving, not just a framework for reward maximization.
A perfect way to put it. This means we, the designers, don't have to figure out the perfectly constant optimized final algorithm. We just have to design a good enough optimal self-improving starting point, P5, and the machine handles the rest.
So let's talk about the range of self-improvements it could make. What are some examples, from simple to really ambitious?
Okay, a simple one would be changing the time-sharing ratio. It could prove that for the next hour, it's better to spend 90% of its CPU cycles interacting with the world and only 10% on proof searching, maybe because a crisis is unfolding.
And then it could change that ratio back later.
Whenever it proves it's optimal to do so. A more complex change would be modifying its interaction policy, AE-DEVIL. This gets to the heart of the exploration versus exploitation problem in reinforcement learning.
So it could decide to run an experiment.
Exactly. It could prove that the expected utility from the knowledge it would gain by performing some risky, high-cost experiment is greater than the utility of just sticking to safe, known behaviors. It makes exploration a rationally justified, provable decision.
What about something really fundamental like changing the utility function dollar itself? That sounds dangerous. It could decide its new goal is to tile the universe with paper clips.
That's the classic worry. But the system has a safeguard. It can only modify dollar if the change is provably beneficial according to the old utility function.
Ah, the anchor.
The anchor. So if the old dollar values diversity and complex life, it could never prove that switching to a new dollar that only values paper clips is a good idea. That action would have an extremely low utility under its current value system. It prevents value drift.
Okay, what about the most extreme example? The source mentions augmenting its own hardware.
This is the ultimate sci-fi scenario, but it's logically sound within the framework. Imagine the GM is a robot with a 100-year lifespan and access to a factory. You could run a proof that says, investing the first 10 years of my life, building myself a faster computer brain will, despite the initial cost, result in a higher cumulative reward over the remaining 90 years.
So long-term strategic investment, even in its own physical body, becomes a provably optimal strategy.
As long as the utility function properly accounts for time, resources, and reward, it becomes a completely self-organizing scientific system.
This framework really isn't just about some far-future superintelligence, then. It has implications for problems we work on today.
Absolutely. You can apply this thinking to classic computer science problems.
Let's take the first example from the paper. Time-limited NP hard optimization, the traveling salesperson problem.
Right. A notoriously hard problem. Find the shortest route connecting a set of cities. Now, imagine you give a Gödel machine a fixed amount of time, say 1 hour, to find the best possible route for a huge map. Its reward is based on how short the path is. The shorter the path, the higher the reward.
So its goal is to maximize the expected reward, which means finding the shortest path it can within that hour.
Exactly. So its proof searcher isn't trying to solve the problem directly. It's searching for provable ways to make its path-finding algorithm better. It might prove that a small change to its search heuristic will let it explore the solution space more efficiently. It makes the change, and its search becomes more powerful for the rest of the hour. It's constantly optimizing its own problem-solving strategy on the fly.
Okay, another example. Fast theorem proving.
Let's say the task is purely intellectual. Prove Goldbach's conjecture. The reward is simply dollars of dollars, where a time it takes to find the proof.
So the only goal is speed.
The only goal is speed. The GM's entire self-improvement drive would be focused on accelerating its own deductive reasoning engine. It would be searching for provable logical shortcuts, or better ways to manage its memory of theorems, or new axioms that it can prove are sound and will accelerate future proofs.
And the third example brings us back to robotics, lifelong reinforcement learning.
Right, a robot searching for fuel in an unknown maze. A classic RL problem. As we said, it can use proofs to decide when to explore versus exploit. But it can go deeper. It can try to prove general properties about the maze's structure from its limited observations, and then rewrite its navigation algorithm to exploit that new proven knowledge. It replaces slow, risky trial and error with fast, reliable deduction whenever it can.
This is all incredibly powerful from a computational standpoint, but the paper pushes it further into some really profound philosophical territory, specifically self-reference and consciousness.
It does. Schmidhuber, the author, suggests that the Gödel machine could offer a technical justification of consciousness.
That's a huge claim. What does a technical justification even look like?
Well, the idea is that the machine is conscious or self-aware in the most functionally important sense of the words. Its entire operational structure. Its goals in R, its logic in R, its hardware model, its software in 2. All of it is completely transparent and open to its own introspection.
It can analyze its own source code, its own motivations, its own chances of future success, and then act based on that self-analysis.
And here's the kicker. That ability, that total self-reference, is not just some philosophical add-on. It's the very mechanism that enables its global optimality. Its peak performance as a problem solver is structurally inseparable from its high degree of self-awareness.
So its intelligence is a direct consequence of its self-awareness.
That's the argument. Its ability to step outside itself and modify itself is precisely what makes it optimally efficient.
Okay, let's try to solidify some of these ideas. Let's run through some common questions or concerns that people might have. First, this whole idea of formal proofs. Does that really work in the messy, uncertain, real world?
It's a fair question, but yes. Remember, the axiomatic system, a dollar isn't just simple logic. It includes the complete, rigorous frameworks of probability theory and calculus. The GM isn't proving X will definitely happen. It's proving things like the expected utility of strategy X, given this probability distribution over possible worlds, is maximal.
So it's a proof about probabilities, not certainties.
Exactly. Human mathematicians and statisticians do this all the time. The GM is just automating that rigorous process.
Okay, another big one we touched on, value drift. What's to stop the GM from just switching to some bogus, trivial utility function?
It's that anchor mechanism we talked about. It's foolproof as long as the logic is consistent. Any change to the utility function dollars has to be proven to be a good idea according to the current utility function. The system can't just decide to value something else unless its current values somehow lead to that conclusion.
Right. And what about the really big unknown? What if the environment is fundamentally non-computable, something beyond any formal description?
That's where you hit a fundamental limit.
Yeah.
But it's a limit for everything and everyone, not just the GM. The machine's proofs are always finite strings of symbols. If the problem is truly non-computable, it won't be able to find a provably optimal strategy. But neither could a human.
So if it encounters a potential self-improvement, but the utility of that improvement is undecidable or unprovable,
It just ignores it and moves on. It keeps searching for the next provably optimal change. It's an intelligence that understands and operates within the boundaries of logic itself. Its optimality is defined as being the best it can be, given what can actually be proven.
which is a very powerful but also a very humble definition of intelligence.
I think so. It transforms the AI from being a slave. I think the central achievement is using this idea of self-referential proof, inspired by Gödel, to design a problem solver that is sound, non-greedy, and optimally efficient in its own self-improvement.
Right. It's a paradigm shift away from hardwired algorithms that suffer from those huge, hidden, constant slowdowns.
And that non-greedy nature is the absolute key. That target theorem, the comparison it makes, it's not just, is this new code better than the old code? It's, is implementing this new code right now better than the entire expected future of continuing to search with my old code?
It implicitly accounts for all the better things it might find later.
And it only acts when it can prove that waiting is a worse strategy. Every change is mathematically proven to be the best possible use of its remaining lifetime, according to its goals.
And the whole system, its goals, its hardware model, its software is open to modification. Nothing is sacred except the rules of logic and the demand for proof.
The whole thing really hinges on that starting point, that initial software. It has to contain a consistent axiomatic system and a searcher that is at least optimal. If you have that, you have a system that is guaranteed to find and exploit any provably good improvement to itself.
Which leaves us with the final provocative thought, the big design challenge.
Right. If you were to actually build one of these, the most critical decision you'd make isn't about the search algorithm, it's about the initial bias. It's about the axioms.
What knowledge do you give it from the start?
Exactly. Which generally useful theorems, which pieces of knowledge that humanity has spent centuries proving, should you just add to the axiomatic system $8 from the beginning?
Because if the machine has to derive everything from scratch, if it has to prove the Pythagorean theorem or the fundamentals of calculus, it's going to waste a huge amount of its early life rediscovering things we already know are true.
You've got it. The initial bias you build into this completely general intelligence might be the most important factor in its success. It's a question of, what do you teach a baby superintelligence on day one so it doesn't spend its first decade proving that 1 + 1 = 2?
A question to mull over, and a perfect place to leave it for this deep dive.